Well, hi, thank you. Well, I'd like to thank the organizer for letting me speak today, and all of you for coming. And well, this is showing work with Veronica Becher, and I'm going to talk about, well, normality and differentiability and why these two words may be connected in some way. The way the talk is organized is like bottom up, so I will start with definitions and trying to do some work with them so everybody gets what I'm talking about and get to the main result at the very end of the presentation. So first, this is one possible way to define normality. Normal numbers or normal sequences are sequences that are statistically balanced. So what we ask first, we define simply normal, that is that every digit has a frequency of the same for all digits, and they are all converge in the expansion of the real number. And for normal numbers, we ask that they are simply normal in every power of the base. Okay, we will, throughout all the presentation, we work with base b. All of this is true for every b. But we are talking about normality just in one base, so this is not absolute normality, okay? Because in some texts you can refer as normal to absolutely normal, actually. Okay. And then the differentiability notion we are going to use is actually not the regular real-to-real function differentiability, but a notion that is more or less similar for functions and sequences. This is because the normality is a notion that applies to sequences more than to actual numbers, right? Because it only relies on the digit expansion. And the thing is that we're going to be working with functions, and if we restrict ourselves to functions that from sequences to sequences that represent functions from reals to reals, we will be getting a lower number of functions to work with, and we want to have a result that is slightly more general. So the regular definition is the one that is at the top, and if the function is non-decreasing, we can rewrite it as the second expression. And so we are actually kind of comparing the ratio between the image of the function and the domain we are looking, right? And everything around the point we are differentiating, which is R in the first definition. Okay? Well, that's why in the definition I specified non-decreasing, because otherwise the measure way of writing it is not true. So what we will do, since we only care about non-decreasing functions, is try to generalize the second part to sequences. So what we do is do a similar job and take increasingly smaller intervals close to x, where x is a sequence. So what we compare here is the measure of the image of the function on all possible sequences that start with the same n bits or n digits as x, with the size of that, right? Well, this part right here is b to the minus n. Yes, this is the first n digits of x, and then anything. And then this is the first n digits of x, and then anything, and the image of f on that set. Okay?
The function can have a zero derivative, but be not constant.
Yes, yes. Definitely. I will show an example. Yes, so actually this differential, I will speak about this later, but it's not a slope of a tangent like a regular differential in real numbers, but more like a growth rate in a more general way. Okay, so the thing is that this other definition, as you can see, kind of forgets about the sign problems that the regular definition can have, right? Because we are using an interval that may have x always in the middle, right? When we do the regular thing, the interval r through r plus h always has r in one side of the interval, and here that may never happen if x is not a rational sequence. So it doesn't end with all zeros or all b minus ones.
Doesn't it look more like Lipschitz or something?
The definition, you mean? Yeah. Well, the thing is that in the context you are working is not really important. I mean, we will be looking with finite state computable functions, So that condition will not make a real difference. But yeah, well now we argue why this definition is an important one, or at least has some motivation. I'm not claiming it's the best definition for differentiable, but since we didn't find any other to work with. Okay, so first let me introduce the finite state computable notion, which is what we use to link these two seemingly different or separated notions. So finite state computable is more or less the same as computable to some extent, but using finite state machines instead of Turing machines or any other more general machines. So a finite state machine in this context works in a fixed base B, and it reads symbols from the input sequence, and from those symbols it can go from the current state to any other state, but these states are finite, right? So it's kind of, you have constant memory to work with, right? And the states represent all possible states of that constant memory, so it's a finite set. And after you read each symbol, you possibly change state with the function delta, and you possibly output something with the function O. Okay, it's possible that you read something and output nothing. And when you go to infinite sequences, it's kind of taking the limit of this. Since these functions are monotonic in the prefix ordering, it's pretty clear that this limit exists, right? So. Okay, so what we ask is that the machine, or the finite state machine, doesn't have lambda output cycles, so cycles of input, so in the graph of states. So there are no cycles that output a lambda, because if we had a cycle that outputs lambda every time, then some infinite sequence will have a finite output, and we have every infinite sequence to be mapped to some infinite sequence. Right. So it's not possible that you infinitely often output. Well, yeah, infinite often, but you always end up outputting something, right? So every infinite sequence.
Lambda means empty string.
Yeah, lambda is the empty string. Sorry. Okay. Also, this is a machine, and the function it represents is this, and so we call a function from infinite sequences to infinite sequences computable if there is a machine that computes it. And if for functions in reals, we say, well, if there's a machine that computes it, but we ask that if we input different representations of the same real, then we have not necessarily the same output, but two outputs that are also the same when seen as real numbers, right? So in here, B is the function that maps the sequence to the real numbers in the obvious way, right? Here is the formal definition. So it's the same to go to take a sequence and go to the real numbers and calculate f, or to first calculate g with the machine and then go to the real numbers. Okay. As you can see, this extra condition is like kind of powerful and restricts a lot the world of functions, right? This has been studied before, so that's why we are going to try to work with differentiables in the first world of sequences to sequences, and then relate it to this second, more restricted world. Okay, so here are some examples. Well, the first one is the one that motivated the question, that, for instance, if we take a function that reads the input, and for each bit it outputs it twice, okay, that is obviously computable with finite state. This is the one that is drawn below, and this function will of course have a differential of 0, because the measure of the image is 0, because it never contains like 1, 0, 1 or 0, 1, 0 or something, right? So since the measure of the image is constantly 0, the differential is 0 at every point, right? But still, since we are mapping digits to lexicographically increasing outputs, then the function is increasing, and is finite state computable, so it fits the definition. Okay, that's the simple example. Then the second example on the right is a division by 2, in the sense that it just outputs the same sequence as the input, but adding a 0 at the beginning. Okay, but the thing I'm trying to illustrate here is not that, because that's computable with a much simpler automata, but you can see that it can be computable with a fully connected automata that always outputs something of the same length as the input, And in a couple of slides below, I will show that it has some interesting properties that make our work with this more difficult. But the thing is that, well, you consider the notation that we can have a finite prefix-free maximal set, which is 1 to the n 0, and we can map each of those to some other set, which is 0, 1 to the n. And if we do that in a way that we can recognize the first set, the input set, with a finite automata, then we can actually compute the function, right? So we can define a lot of examples in this way. In here, all examples are defined this way. So in the left side, we take some prefix-free maximal set and we map each possible thing to something. And the thing is that if the output, so the right side, is also prefix-free and maximal, then the image with the function will be surjective and the image will be 1. And but that's not a necessary condition. So that's of course a sufficient condition, but it's not necessary. Actually, the division by 2, well, it's not surjective, but it has positive measure. But the output of any of the possible inputs in the restricted sense is not a prefix-free set. Okay, because actually every possible output is a prefix of the form. So that's bad for some reasons I will explain later. And then the last example is this: we read, and every 2 bits we output something. Okay, and so we have here some prefix-free and maximal set, and so this actually specifies a function, and this is one way to compute it with finite state automata. So if we start here, and if we read 0, we output nothing, and then we decide from the second digit what we have to output, and if we read 1, then we already know we have to output 2 ones, and then we decide the final output when we come back with the second digit. Okay. So the machine is really simple, and well, the thing here is that since this is also prefix-free and maximal, the measure of the image of the function is also 1 at the beginning, but we will see that for the differential this has like a complicated behavior.
Why is that map called compressive?
Oh, because it kind of the inputs that have too many zeros, so more zeros than ones, will kind of behave in a way that, so it compresses finite strings that have too many zeros. Okay, more than half or a little more than half. Okay. For infinite sequences, it doesn't compress, but it kind of the growth rate of this depends on how many zeros, right? If you have too many zeros, you will end up making, influentiating bits in the output that are much below the bit you are reading, right? You are reading the nth bit, and you can be outputting the n over 2 bit or something like that. If it has too many zeros, if it has a low number of zeros and too many ones, the other thing happens. Okay. Okay, so this is what happens when we apply the differential definition to a finite state computable function. So first we take the little f and we define a big F that computes it because it's finite state computable. And just for technical reasons, we define an f sub q, which is more or less the same machine but changing the starting state. Okay, because it's easy to work with this. And then in the first line we have the regular definition, and then applying the definition of the function computed, then we'll have the measure of, first we'll have the output of the first n bit of x when passed through the machine. Okay, and then we will have the same function but possibly changing the starting state. Okay. So if we apply the function to the first to a string that starts with the first n symbols of x, we have of course its output, and then, well, the rest. Okay. Well, then the next step is trivial. It's just, well, since we know what we have at the start, we can put it out of the measure. And the good thing is that this part right here only depends on this state. Right? The only thing that it has about x and n is which state is this. Okay, so to emphasize this, I write this as a constant that depends well on the machine and the state. Okay. The good thing is that this will only this can only have a finite number of values because one for each possible state of the machine. Okay, so that gives us something to work with. Okay, so so let me let you know some of the difficulties to work with this kind of definition. So the first thing is that previous work with finite state things related to normality always use like superior limit or inferior limit to define compressibility, and well, that's bad in some cases, but it has some good properties. Like, well, let's take a subsequence of positions and just care about what happens there. And in particular, the usual trick used in many previous papers is that, well, let's take a large k and see what happens after a block of k digits. Right? We cannot do this here because since we have regular limiting definition, we have to take care of oscillations in the middle. So that's a problem. So what we do is, instead of using blocks, we use the cycles that go through the same state. Because since we know if when we return to the same state, the value that the mu sub f and the state will be the same, right? So we can take care of that. The thing is that the set of cycles that goes through a state has a good property, which is that the input strings that provide those cycles is maximal and prefix free. So that's a good thing to work, but the problem is that the output is not. So that is illustrated by this example, which was also the example I showed before, right? So we have all the cycles of the state here, which is a prefix free and maximal set, but the output is not. So we do want in the middle of the proof some properties that prefix free sets have, and it will be a good thing to prove that it is. This forms a prefix free set, but we have to go around it and make some more complicated things to be able to do that. So that's one of the first difficulties we find. And the other is that this oscillation happens in a strange way. So this is the example that was at the bottom before.
What property you want to prove?
Well, when I get to the proof, well, because the thing is, I won't be able to show the entire proof because it's long and technical.
What statement?
But it's, well, I didn't say it yet, but these are like in general difficulties in general to work with this kind of definitions. And okay, I will have a statement later. Don't worry. So the other one is that we can have these like strange oscillations for like really simple examples. For instance, if we, with this example, if we have this input sequence, well, it will oscillate because at some points it will be in different states, and in each state it will have a different value. So I won't go through the math because it does oscillate. But the good thing is that if we have a finite number of states, what we will be able to prove, and we prove as an intermediate result, is that the oscillation is through a finite number of values. Okay, because the mu sub something is finite, can have a finite number of values, but also the difference between n and the output of the first n digits of x can also have only a finite number of values unless it diverges or goes rapidly to 0. Okay, so now this is I want to motivate why the definition of differential I mentioned was a good definition, or at least an appropriate one. So this is basically, if the differential is different to 0, I can take the logarithm and we obtain the expression that is there. So what you can see is that the term measuring the image of the function from each possible starting state in the machine actually is like a correction term that measures how much the difference can be between the input, the number of input and the number of output. Okay, so it's like three things can happen. If the input grows, if the output grows too too fast with the input, then the entire differential will go to 0, because the first subtract, well, not in this case, but so if the output grows faster than the input, then the differential will go to 0, because the first part will go rapidly to 0 and the second part is bounded. Okay, the bit power to something will go to 0. If it's the other way around, if the output grows not faster than the input, then this will diverge, because the mu is also lower bounded by 0. And well, there's other border case in which if the measure is 0, then the differential is 0 and that's it. And then in the other cases, the oscillation between the growth of the input and the output can be measured by this factor right here, the logarithm of the constant. Okay, so in some way this kind of measures some information at the store at Q. Okay, so the machine kind of saves some information in Q and outputs it later. Okay, so if this is high, if the minus logarithm of m sub f and q is high, it means that Q has like a good number of bits stored in it, so with less input I can output more. Okay, so this kind of adds up to the difference between input and output. Okay, and this proposition, which we can prove, is the one that actually provides the motivation for the definition. So well, if the differential has a value that is greater than 0, it means that this value should be something like the growth rate, right? Because that's what it means in regular real-to-real differential functions. So if the growth rate is k, what should happen is that the first n bits of the input influentiate at most let me fix the first n minus the logarithm of k first bits of the output. Okay, that's kind of, well, how much can I influentiate the input, right? So if I change the, I don't know, 10th bit of the input, then it can change the first bit of the output or something like that. Well, this is all for sufficiently large n, because we need to be around the point we are differentiating. Okay, so these are two ways to write the same. And this is more or less saying in a sequence language in which we only have digits and a step, but it's more or less saying that the differential is the slope of the tangent or the growth rate of the function. And of course, if the differential is 0, it means that the growth rate is asymptotically 0 in some sense. So for any constant, we will be able to compute n plus c bits of the output just taking n bits of the input, right? Because, well, if you think about it as a constant function, if I have a constant function, I don't need any input, or I just need a fixed amount of input to calculate the whole output. Well, this says this in some sense, right? It's not necessarily constant, but for instance, if you think about the example of the doubling bits at each point, then with n bits of the input, we can calculate 2n bits of the output, right? And we can have examples that the output grows slower, which, for instance, we take 5 bits at a time and output 6 bits, and then with n bits of the input, we can calculate 6/5 of n bits of the output, but still, it's always a little more output than input. Okay, you can also see this as well. If we take the logarithm of 0, it's a kind of n minus infinity, so this minus infinity there is replaced by, well, plus c, where c is any constant as large as I want. Okay. Okay, so this is our main theorem. The three things are equivalent. One is that for a sequence, the real number represented by the sequence is normal. That every non-decreasing function, finite computable, is differentiable at that point. This is for functions from sequences to sequences, and for functions from reals to reals. Also, the working in machines from the base in which we know the thing is normal, they are also differentiable as v of x, right? So this is kind of another version of the Lebesgue theorem, and that there is a recent computable version. Okay, so I think I don't have time, but I have some condiments about the proof, but it's kind of long, so I will skip it, in order to save time. So the first direction, the first implication is the hard one. Sorry? Oh, b of x is the real value of the sequence x. So it's the summation of the inverse powers b. So let's keep it. Oh, so this is to sum up the result we want to present is that, well, we have the Lebesgue theorem that is for non-decreasing functions are differentiable in almost every real. Then we have the computable version from Bragg, Miller, and Nice that says, well, if the functions are computable, then this almost everywhere can be precise as computable random reals. And, well, our version is that, well, if we have functions that are finite computable, then this almost everywhere thing is precise as very normal numbers. Okay, and this right here is always dependent of the base. So for each base we have this, because it's not the same to work in with finite state in base 2 or 3, and that's reflecting on the fact that normals in base 2 are kind of independent from normals in base 3. Okay, and here are some of the main references that we use for a proof that I didn't present. But, so these are just the references that are directly used in the actual math that the proof that we did, not everything that is related to the problem. So that's it. Thank you.
Questions for Pablo? Steve?
What about functions that are not increasing? I mean, that can functions that can increase and decrease. I mean,
Yeah.
Continuous function.
Well, we haven't investigated that, but with this, I mean, I think even the definition I gave for differential is not appropriate for functions that are increasing and decreasing. But for instance, it's easy to construct a function like, for instance, if you take a function that takes that behaves like the identity at even positions and complements the bits at the odd positions. So it takes 0, 0 to 0, 1, 0, 1 to 0, 0, 1, 0 to 1, 1, and 1, 1 to 1, 0, right? So complements every other bit. So this function is not differential anywhere because it oscillates heavily at every possible place, right? So if you take a cone, so if you take this with even n, you will get like one behavior, and with odd n, you will have some other behavior. So the limit of anything, so the limit of this will be oscillating every time. Okay, so it's kind of difficult to even define a good differential for this.
Why for this?
Oh, but because I mean.
So is that function on, when you translate that to a function on the unit interval, is it continuous or is it differentiable?
This is the problem.
This is not a real function. I mean, you can regard this as a real function because it doesn't. I mean, if you input two different representations of a rational, it doesn't output the same real.
Okay.
Okay.
So we define the counters.
Yeah, this is defined. Well, this is actually two. Yeah. Yeah, but the thing is that, well, I don't actually know what to define here. But I mean, for instance, if you try to do something like this, which was the first attempt, 1 to the omega and subtract in some sense, right? So this is like something that reflects the f of x plus something and f of x, right? So this is like the highest and the lowest thing you can get after m digits. So this subtraction here oscillates because this part here will get mapped to 0, 1, 0, 1, 0, 1 sometimes, if n is even, for instance, but in the other cases it will get mapped to 1, 0, 1, 0, 1, 0.
So what? You have the interval of all which starts with x given n. And
Yes.
it's mapped, this image is exactly the interval of the same length. So the definition, in your definition, it's not one? I don't understand. The definition probably.
Oh yeah, okay. Well, with our definition, this is this does not oscillate. But what I meant was that, I mean, let me go back. Okay, so the second definition for the real-to-real function only makes sense if the function is non-decreasing, right? Otherwise, it's
Why?
oh, because the subtraction there is not equal to the measure of the image of f if f is not non-decreasing.
Even if it's not non-decreasing, it's also not the image if the image has holes.
Yeah, of course, but okay, let's even restrict ourselves to continuous functions. Okay, the problem is that when I do the measure thing, I forget about the sign of the subtraction. Okay, that's the main problem, because I can say, well, okay, let's only do this for continuous functions. Okay, so no hope. Or no important, but still, I mean, forgetting about the sign, it's okay as long as the function is non-decreasing. Because if the function is non-decreasing, we know that there will be no problems in which the differential will have like a value of plus alpha from one side and minus alpha from the other side.
This example, can you repeat? This example illustrates what? So you give some function as an example of something, but can you say again this example of what problem?
Okay, so what maybe something I would like to do, or maybe is do something like this, right? So take the value of this and the value of this and subtract, and this is more alike from the original real numbers definition than the one that I used. Okay? Something like this. Because it has a subtraction.
If the function is not on real numbers, what is the...
Well, that's the problem.
How do you combine this with...
Well, yeah, that's the problem. But the problem is that if finite computable functions and the real numbers are really stupid. It's like piecewise linear functions, and that don't have much interest. And this kind of definition for differential at least has the interest of, it's kind of an oscillation control of the compressibility ratio. Okay. So if you look at here, if the finite state machine is compressing the sequence x, then this will go to infinity, okay? Because n minus the length of the output will not be bounded, so this limit will diverge or oscillate, but at least it will not converge to a finite value. Okay? That is the case if the finite state machine is compressing the input. And then, if it is inflating, it will go to 0. But if it's neither compressing nor inflating the input, then this sequence of values for each n provides a control of how much the oscillation can be between the input and output length of a machine like this. So
I'm gonna butt in here. I think this is a good topic for lunch conversation, so why don't we leave the speaker?